So previously we have talked about atoms, what makes an atom. We've looked at closely at the different properties of atoms. Let's get started into looking into what happens when atoms chemically combine with each other to either make molecules or formula units. In other words, we will talk about now how chemical bonds are formed, how and why chemical bonds are formed. We will look into the two main kinds of chemical bonds, ionic bonds and covalent bonds. So before we actually talk about the chemical bonds, a couple of terms that we need to define and understand and then start using, because these are the best ways in order to figure out what kind of a chemical bond a certain atom would be more prone to make under given conditions. These terms are valence shells and valence electrons. Now, earlier on, you may recollect that in one of our sessions when we were discussing atoms, we said that the nucleons or the subnuclear particles are protons and neutrons, and protons and neutrons are the particles that live inside of the nucleus in the center of an atom. But what's on the outside of the nucleus? Absolutely. All the electrons of the atom live outside of the nucleus. They occupy that space of the atom, and they're constantly moving around with each electron having a negative charge, and of course each proton with a positive charge. But when we looked at that structure of an atom, as I said then, that was a very simple starting point for the structure of an atom. Electrons do not move around the nucleus randomly. They do have specific areas of space where the probability of finding those electrons is pretty high at a given time. Every electron has its own characteristic energy, which then decides what kind of an energy shell, so to speak, would that electron live in outside of the nucleus. So at this point, maybe bringing in the picture of an atom where the nucleus being in the center of an atom, and then there are shells of space, shells of energy, basically concentrically growing bigger as you move away from the nucleus. So every shell has an energy associated with it, and depending on the energy that the electron has and how it matches up with whichever shell it's present in, the electrons are arranged in the atom. So valence shell is defined as the outermost shell in an atom. Valence shell is the energy shell that contains electrons. It is occupied by electrons farthest away from the nucleus. It has the highest energy. The energy of the shells increases as we go away from the nucleus. So the shell closest to the nucleus has the smallest energy or the lowest energy. It is most stable. Lower the energy, please remember, higher is the stability. So the first shell is the most stable, and then the energy increases as we move away from the nucleus. So the valence shell is the outermost shell. It's the shell that's farthest away from the nucleus that has electrons living in there. Now, the ability for us to figure out which shell is the valence shell can get complicated depending on the electrons, but for representative elements only, now if you remember, the representative elements are the elements in the A category of the periodic table. For representative or main group elements only, actually it is pretty easy to tell which shell would be the valence shell, because the valence shell is equal to the period number in which that element resides in. So if you look at the periodic table that you have handy, calcium is in period 4, and therefore the fourth shell of calcium atom will be the outermost shell. Let's take tin. Tin is in period 5. Therefore, that shell will be the valence shell for tin atom. How about oxygen? What is the valence shell for oxygen? Exactly, 2. Shell number 2, because oxygen is in the second period. How about lead? Lead is a symbol Pb, and it is shell number 6, that is the valence shell for lead, because lead is in the 6th period. So for main group elements only, the valence shell equals the period number. Now, when the electrons are distributed in these different shells, they are distributed based on their energies plus also the capacity of each shell. Not every shell is equally capable of, not every shell is capable of holding equal number of electrons. The smaller the shell, the lower would be the capacity. I mean, that's what we intuitively think. Now, as far as atoms are concerned, that is the case definitely, that the smaller the shell, the closer the shell is to the nucleus, the smaller the shell is, the lower is its capacity of the number of electrons it can hold. So if you have, let's just get an idea of, if you have certain number of shells, then what would be the capacity? So the first shell, the shell closest to the nucleus that has the lowest energy, cannot hold more than 2 electrons. That's its capacity. It's full once 2 electrons are placed in that shell. The second shell from the nucleus has a capacity to hold a total of 8 electrons. The third shell has a capacity to hold 18. The fourth shell has a capacity to hold 32, so on and so forth. There's a reason behind these numbers, and that is beyond the scope of this class, but you'll talk about it later. But if any of these shells, beyond, any shell from shell number 3 and above, if that shell happens to be the valence shell, then the capacity for that shell is only 8. So the other term that we need to define and understand are valence electrons. Valence electrons are all the electrons that are present in the outermost shell, in the valence shell. For example, down here at the bottom of the slide, I have shown an atom. Now look at closely at the atom and count the number of electrons. The central dot, of course, is to symbolize the nucleus, and the dots in the shells, 3 shells, symbolizes electrons. Now note that there are 3 shells. If there are 3 shells, which period do you think this element is in? Absolutely, the 3rd period, because the 3rd shell is the outermost shell. Now count the number of electrons and then go ahead and tell me which element is this atom representing. Exactly, it is representing magnesium, because magnesium has a Z value equal to 12, which equals number of protons. But since number of protons equals number of electrons, this atom should also have 12 electrons, and that is magnesium. So when we distribute the 12 electrons in the magnesium atom, 2 go in the first shell and the first shell is full, 8 go in the second shell and the second shell is completely full, and the remaining 2 therefore end up in the 3rd shell. Those electrons, those 2 electrons that are in the outermost shell, the valence shell, are called valence electrons. Now once again, as the atoms get bigger, this distribution of electrons in the shells gets pretty complicated as well. So without going into the detail of that, for main group elements only, for representative elements only, it is once again pretty easy for us to figure out how many valence electrons it has, because the number of valence electrons equals the group number. Please remember, earlier on we decided we will only use the group number in the periodic table that has a letter attached to it, either A or B. For main group elements, of course, that letter will be A, and therefore the number that goes with the letter A is the number of valence electrons. So once again, as we said, this is magnesium atom. If you're looking, if you're looking at magnesium, which has a total of 12 electrons, the valence shell is the 3rd shell, because magnesium is in the 3rd period. The number of valence electrons is 2, because if you look in your periodic table, magnesium is in the 2nd group, 2A, and therefore we can figure it out without having to do electron configuration, or without having to do electron distribution into the shells. So we in this class in Chem 140 will only be using this general guideline once again to emphasize the general guideline. For representative elements only, valence shell equals the period number that the element exists in, and the number of valence electrons equals the group number that the element exists in. In order to make the representations of these elements very convenient, we will use something called a Lewis symbol for elements. It is a very quick representation which shows the elemental symbol for the element, such as sodium is represented, of course, as Na, uppercase N, lowercase a, with its valence electrons represented as dots around it. Now, sodium element, how many valence what is the valence shell for sodium? Number 3, because sodium is in the third period. How many valence electrons does sodium have? Sodium has only one valence electron because it is in group 1a, it's an alkali metal, and therefore that one valence electron is represented as a dot around the symbol. This is a Lewis symbol for element sodium. Does this mean that there is only one electron in the sodium atom? No, it does not mean that. Sodium has a total of 11 electrons, but out of those 11, only one electron exists in the outermost shell, the valence shell. Okay, let's try out quickly writing the Lewis structures for these elements using the same idea. So bromine is in period 4, in other words, the fourth shell is the valence shell, and since it's in group 7a, it has 7 valence electrons, and therefore we can represent those electrons as dots around the symbol Br. We try to place the electrons around the symbol in pairs because electrons like to live in pairs as much as possible. Carbon is in the second period, in other words, the valence shell is the second shell, but it has 4 valence electrons because it's in group 4a. So yes, we can write those 4 electrons like this, or you can write those 4 electrons like that, or any of those is fine. Lewis symbol doesn't really care about the shape or, in fact, you can't anyways tell the exact placement of electrons. Aluminum has 3 valence electrons in the third valence shell, and therefore this would be its Lewis dot structure, or you can even write those 3 electrons standalone. Lewis structure is really not a very specific structure, but it does give us, it's a very quick shorthand representation of an element showing its symbol and the valence electrons. Why is it so important for us to know valence electrons? And that is a very important question. It is important for us to know valence electrons because when chemical bonds are formed, it is only the valence shell and the electrons in that shell, in other words, valence electrons, participate in bonding. The electrons in the inner shell that are called core electrons do not participate in chemical bonding. Only valence electrons do that. So that is why it is extremely important to know how many valence electrons does a certain atom have. So when all atoms basically when they undergo chemical bonding, we assume that they are trying to follow the octet rule. Octet rule is a good starting place for us to start understanding chemical bonding. You will of course discuss this in way more detail later on, where you'll talk about lots of exceptions to octet rule. In our class, however, we will not deviate from the octet rule. So the octet rule says the atoms lose, gain, or share electrons, valence electrons, please note that term, in order to achieve a stable noble gas electronic configuration. Now, if you remember from a previous session, the group 8a in the periodic table, the group to the rightmost edge of the periodic table, 8a, starts with helium. That whole group, that whole family is called the noble gases or inert gases. They are inert, meaning unreactive. For most part, they do not make chemical bonds because they are happy for most part being whatever they have. They are noble because all the other elements are trying to achieve the nobility that these guys have reached already. They're trying to get what they have, which makes them stable. And that is the basis of the octet rule. The thing that all of the noble gases have, the feature that makes the noble gases so stable, is the fact that their electronic arrangement in the atom ends up giving them what we call a full valence shell. In other words, the valence shell has 8 electrons in them, except for the first period, for the first shell, if that happens to be the valence shell, because the maximum capacity of the first shell is 2. So if the valence shell is the first shell, then the maximum capacity is 2. But if the valence shell is anything else above that or beyond that, then the maximum capacity would be 8. And noble gases have that. Helium has 2 electrons in the first shell, it's full. After that, neon has 8 electrons in its second shell, that's full. Argon has 8 electrons in its third shell, and that's full. That is what we call a full valence shell, and that gives a tremendous amount of stability to those atoms, which makes them pretty inert, unreactive, do not want to form chemical bonds. So all other atoms will either lose, gain, or share electrons, their valence electrons only, in order to achieve that same electronic arrangement. In other words, atoms will lose, gain, or share valence electrons in order to have 8 electrons in their outermost shell. Except, of course, when the outermost shell happens to be the first shell whose capacity is 2, and then it's considered to be full. This is the octet rule, and the octet rule forms the basis of chemical bonding, and this is the rule that we will follow pretty strictly for our class.